Welcome to PyData Global 2021. We're here with Saul, one of our many amazing, multi-talented data scientists, and I'd like to and since this is his time, I'd like to just cut straight to handing the mic off to him. You can take off.
All right. Well, I'm Saul, guys, and so this is my first time kind of presenting over at PyData. I've attended the conferences before in the past, back in my home, or one of my hometowns of Austin. Today I'm gonna talk about like why I learned Python in the first place, and then how I'm using it today. And so I first picked up Python like around 11 years ago, like Python 2.2, 2.3. So I've been there through like the great Python 2 to Python 3 migration, and that was a hellhole. But Python is kind of becoming this more common like interpreter language that we all use a lot in our day-to-day. And the reason why is because you can kind of turn these layman term objects into something simple in code, and it reads somewhat similar to English, but there's some like weird funky things, as we all know, in Python. And the chart I'm kind of showing you comes from back in the 80s, and what they were trying to demonstrate is that all these languages that we create, whether it be code or something like English, it's still inherently like man-made. And so in the past, they used like things like Fortran and BASIC, and they did all these like mathematical functions and like wrote all the mathematical notations into these codes. And then they also like, you'll see in the old chemical companies, they were writing like all the different notations of chemistry as well, like chemical machine representation using these languages. And at the same time, well, this comes back from the 1800s and now forward, but IUPAC was developed so we can call chemical compounds something that kind of fit to like alphanumeric like languages. And so, but then what's happened in our generation of millennials, we like a lot of slang, and we talk with fast words, and we type fast, and especially in the lab too, we like to talk fast. And so the IUPAC nomenclature, we've kind of turned it into what we call a preferred name, which I really think is like slang, but we kind of have this formation of like languages. And Python is now installing itself as like the main kind of like vehicle that we can kind of like communicate these languages to each other. And so I want to highlight like this is from back in the day, like 2005, like the old Python logo I think I found online, and I was just like, wow, it really iterated. And from there, there's a lot of different other software all involved, but into what this project really is. And so I want to start from before I picked up code, I was an organic chemist, and I spent a lot of years in the lab running reactions day after day. And so that's just what we like to do. The most prettiest thing I've ever seen in the lab is the thing on the right. This came after the first step over at my time at MD Anderson. It created this beautiful orange color. So it just really shows you how beautiful chemistry can be. And so in my mind, you know, the data and the way we portray data should reflect the same way as something natural like this. So what happened is that I quit my job about a year and a half ago, and decided to go back to academia because I wanted to go, I guess, understand like chemistry a little bit more in detail and see how I can really apply it. So yeah, I went into academia and I came to Baltimore, and it turns out when I came to Baltimore in January, I came across this group, and they developed like these force fields, and I'm like, okay, what are force fields? And so I went into this long history about what force fields are, but force fields are inherently like a way to describe the movement of the atoms and the geometry of atoms, and how and where and what position they're going to be, and kind of demonstrating that flow. And there's like a series of numbers that kind of like corresponds to all the different atoms. Now, there's different formulas that exist. In Baltimore, we have one of them, and the name is called CHARMM. And for this presentation, you guys are all just going to believe that ours is the correct one, because that's what I believe in. So, and what I'm showing you here is that when we try to like guess how these atoms move in space, we try to guess like kind of a series of numbers. We do it manually. And you can see on the green dot how many manual numbers we kind of guess to kind of like help predict, like, okay, these atoms move like this and these move like this. And the red ones are determined from like a calculation. And so we categorize all these different atoms. And so we have like a series of elements, if you guys have all seen the periodic table, but then we kind of branch it out into like different categories of these elements, because they're representing different scenarios. And in the bottom, I'm showing you the different classifications of what we use as tunable things. Like bonds, it's like the spring constant. And the spring is something you guys all know from physics, right? Like 1/2 kx squared. Looks very similar to here, right? So it's just basic force constants and these basic physics that kind of govern all of this. The seventh term, Leonard Jones, I'll get to in maybe a year from now. So we look at all these series of numbers and we try to predict something, and then we try to figure out based on their atom scenario. And what happened is that I think, if I get the year right, is 2014. They came up with a language to kind of describe this, and it if you see what this language really represents, it's everything that they've done with the quantum mechanics data and the molecular mechanics data and all those numbers, and they've condensed it all down into this language. And they call this language an atom type language. So you'll see a series of languages accommodate different equations. And so we're looking at the CHARMM General Force Field language, which is depicted here on the left. But to make this represent back to something that's chemistry, we actually have something here on the far right-hand side, which is more English-like, something that's just alpha characters or something in that series. This group of atoms, like this is how we were taught as undergrads. And so like we can understand a lot of things that come from this because we can use it to connect to other things using causal inferences. But to combine these two languages together and to create that type of language link, we had to go through a series of other languages first, which is a little complicated. But luckily, the to atom types connector was actually already written here in Baltimore by a coworker of mine. The smallest of smarts was written in Python in London, and the smarts to IUPAC was written by me, also in Python. And so Python kind of served as a vehicle to talk between these different languages. I actually used the sub-process around this locator right here, so you could say it's Python again. But then to make these connections, we're going to have a lot of different types of data, because if you think about it, a group of atoms is just one name, whereas like each atom has like, you know, a lot of, it depends on how many atoms there are, but there's a lot of different names in there. So we're going to have a lot of different type of data. Plus, we also need to understand what are we looking for and what question we're trying to answer. And what we do when we start developing a force field, we have to do something called parameterizing. And parameterizing is inherently like, sum it down to one word, we're trying to fix the force field. And so we need to know what to fix. And so what we're looking for is what to fix. And so to answer that question, my boss and I came up with a series of different features we deemed would be relevant to answer that question. The first would be like, what groups are in there? And then the second is what different types of groups are in there. And then there's these penalty scores. And these scores are telling you what's wrong. the higher the score is, the more that thing magnitude needs to be fixed. So like we need to go after that first because it's a little bit more intense. So this penalty score, this is kind of a beautiful architecture which you could always apply to a lot of other things. So this penalty score is what makes our equation kind of unique, because when we guess something wrong, we need somewhat of like a feedback loop, a feedback saying like, how wrong did we actually guess this? And this penalty score is based off of something simple. So if you look at your file organization and you say that like, okay, I'm going to a picnic, right? And you take a lot of pictures at the picnic, and you do that July 2019. And then you have image 1, so .jpeg. And then you do another picnic, July 2020. And then you have another image. Let's say that you have another file, you took another picture, so 3.jpg, and then you want to place that file in your 2020 over here, but it actually goes in the 2019. So this is actually supposed to be with 2020. Now you research for your files again, and you don't find it. So every time you search through something, that operation right there is actually a contribution to the penalty. So it's like an inefficiency. And so we have these like series of numbers that we deem as like, if the organization is bad, or if it's like, we've done too many operations of some type of kind, and like, it causes these different magnitudes of the scale, it produces this type of penalty score. And that to us is like what we feel is, if the atom types were organized in accordance to whatever is the best representation, then theoretically, when we do collect all the atom types, the penalty scores of all of them should be 0 if we ever approach that type of scale, because then our organization of the atoms would be the best. So we organize our atoms in exactly this kind of way, using categories and subcategories. The penalty score, though, when you start pushing it to an extreme, you can just take that series of numbers and take it as a list, and you just take the probability density. So where do the numbers like to lie is what that's really saying. And you can do it associated with all those different classifiers. And you find out that they start creating these weird valleys. So the algorithm, as it starts pushing into the stream, like creates these weird valley networks that maybe we can use to separate data. And one of the ones I've done is over here at 150. And so what I said is that what I noticed is that things above 150 tend to look a little bit more complicated, and maybe something interesting. And that's all I'm really saying. But I'm still trying to figure out if that's true. So that visual architecture you saw before, I want to talk about why I chose doing sunbursting. So the idea came from here. My old mentor was a DevOps engineer, and he taught me a lot. And he was like, "So you're dealing with a lot of data." And I'm like, "Yeah, I'm always full. I don't know how to organize any of my data." And he was like, "Here, I bought you this." And he bought me something called Daisy Disk. And Daisy Disk, I was like, wow, it's actually really beautiful. And I can organize my data in such a way and see where to look to go for things. And I looked into the history of what this diagram really is, and it's called sunbursting. And then I looked up who does sunbursting in Python. And then Plotly was the main contender there. And so Plotly had this way of just doing interactive sunbursting plots. And I'm like, okay, if I could rig the Plotly and have it have the lexical keys that I'm looking for with different types of languages, I can make this work. And so I'll show you it right here. So the first layer is in correspondence with like the different groups of data that's in there. And then the second layer is the relations of the groups. And then anything that's burnt orange, if you see, is considered something that's 150 or above. And so that's where I'm saying that the penalty score is really high. And so if I click one layer deeper, it makes it a little bit easier on where to click inside the data. So I go deeper in, I go deeper in. And now I know that a high cyclopropane, cyclopentane, and this atom type CG3RC1 is something that I should look into. So I should look into functional groups that contain this atom type because they tend to have something wrong with them. If I fix this, this should stop burning orange. And so that's great. You know, I create a plot and I have this information, but how do I now make this useful? And so I needed to come up with a way to query the graph as well. And so I kind of came up with query functions that accommodate these Plotly graphs. And you can kind of see here, it's just like, okay, if I query, this was it was kind of bootlegged and I was building it as I go pretty quickly. But I didn't know what filters to add initially. So the first ones I thought were like anything high I would like, and then any functional groups. And then later on, we added filters of like the weights and then the atom types and the list of different atoms we'd be interested in. And so here I'm pulling out a query of this atom type and these functional groups. And it responds with the penalty, as well as now their organic chemistry depictions. And so this is a skeletal diagram. This is how a lot of we're taught in chemistry, how to draw our molecules and how we can kind of talk to each other about what's going on. And so we can get a lot of information from just looking at this. And so, so now, right, we come up with this queries and we start generating this list. And so I needed to generate this list of things that are interesting or things that I thought would be interesting. So I rapidly just clicking through and then selecting compounds. And then one week I went to my boss and then I said, pick one. And so I might open it up to the floor. I don't know if you guys can talk or if you guys can put it in the chat, but I was wondering if you guys would like to pick one or just say between A through H. I see more for H. I see E. So to move along, I actually picked E because I thought it was pretty interesting. And I thought it was like a weird structure and kind of complicated. But F, you picked Stephen F, which is why my boss picked it. Or he also picked it. Can you give your reasons to why you picked that?
Not really. It's just sort of a gut feeling.
Yeah, it's kind of an instinct, right? That's the hardest thing to code. Usually when I do this type of slide, it's you kind of run off your instinct. And so that's what kind of separates between machine and human. But he kind of told me his rationale, and it is a pretty interesting one. It has a rotatable bond, a single line right here. And it's very like separated. And so you could like fragment this like nicely. Plus this is kind of an interesting, simple thing. If I look at this looks a little bit more complicated. I don't know what's going on here. There's like a lot of, letters and lines and numbers. And then, this kind of looks like the most simple one out of the bunch. So we chose that one and we decided to work on it. And so that's kind of where I've ended the talk for now. And you can see here I've actually tattooed one of the fragments to my arm. And so, because I really enjoyed parameterizing that compound, and this is something that's really dear to me. So in my spare time, I've been doing this for years, but I write a lot of chemistry to Python packages. So I write a lot of regex in my spare time, which is not common amongst the newer coders. And so I do that for string submatching and testing out 1D languages. And so cocktail shaker, I did that for peptides. And then chemistry, I tried to link SMOS to amino acids. There's mole PDF, I did the SMOS to PDF. And that's kind of a weird way. So there's a lot of like weird and interesting Python code that you guys can like play around with, and it's all open source. And to kind of end my talk, there's a lot of people that have given me advice. And so Alex kind of serves as my boss, and he has given me a lot of great advice on how to, really make my code useful to him and maybe perhaps the masses. And then a lot of people have helped me along my journey in understanding different components. Diesel's the one that taught me about sunbursting, and Sun One here has given me ways to like validate a lot of my code. And then this guy Pauline, he really knows how to manipulate numbers, so definitely someone to check out for. But yeah, if you want, for the last 5 minutes, I could walk you guys through the code if you want to see it.
Yeah, we'll do that for we'll do that for a few minutes to see if anyone's just typing up, and then I'll
Sure.
switch over to our next speaker who's in here.
Yeah, so this is the first or second version, but I've moved on from it. But I made it releasable for now. It initiates as like an object, and it's actually very simple. So Plotly likes to do things in ideas of like 4 lists, and then they map out different lists with each other. And so it actually looks like something like this, where you have like a value 1, 2, 3, 4, right? Or it could be like A, B, C, D. And then what we say is, actually, I'll do A, B, C, D. So let's do a list of A, B, C, D, and then another list of E, F, G, H. This list we'd say is our parents. This list we say is our children. And it just goes by index order, that this is 0, 0 parent, 1 child, 0, this parent, this child, this one, this one. If you wanted it to have like multiple parents to 1 children, you would be like A, B, D, D, and then you'd say G and H are both children of D. And so you can kind of just play around with this like manipulation of lists. And so essentially the graph is just 4 lists, labels, parents, the values, so the size of it, and then the colors. And so I create each list individually. So it goes through a series of data mines, which I call first layer, second layer, third layer, and the 4th layer data mine. And in the end, in the visualization, you just throw it in there, labels, parents, values, and then the colors. And so the plot is actually a pretty simple plot because they've got the sunburst. The idea is just putting it in their data structure way. I was so angry with wrapping my head around that initial concept first, but now that I think I understand Plotly in a very beautiful way. So that's my favorite package. Cool. Yeah, I highly recommend Plotly if you guys ever want to create weird interactive or large data plots. But yeah, it's just 4 lists.
Yeah, thanks. Oh, thanks for being a speaker. So like the combination of like programming and chemistry, it's like you're touching on concepts like I can't even barely begin to verbalize. You enjoy the rest of the conference?
Definitely. All right. Good guess, Stephen. I mean, you made it through. So on slide 8.